These videos?
Yes.
Oh, you watched them? Wow.
Yeah, they're really fun.
Okay, guys. Remind me where we left off. I know we had a few questions like in the 20s. Okay. We're not gonna, obviously, I want you guys to I'd like you to do as many as you can on your own. But I want to go over, I think for this video here, I'm just gonna go over one more example in the 20s or maybe the low 30s. And then I want to go over, if you read ahead a little bit, you might have noticed that 33, 34, 35, and 36 are a little bit distinct from the other ones. Maybe you didn't notice, or no, they're not really more difficult than the other ones. In fact, a lot of people think those are easier. So I think I'll go over one more example, and then I'll go over like 33, I guess. So let's go over. We already did 26. Let's do 29. That one seems pretty cool. 29.
It's actually kind of lame.
It's not, AJ. No. It's actually very lit.
I think this class was really interesting.
Oh yeah, the class is interesting. Do number 29.
Specifically.
Only
not.
All right, so 29. You guys know the first thing we're going to do? Yes. Augers indeed. Okay. So that top is going to factor. We go, okay, what two numbers? Let's see. They got to add up to -2, multiply to -3. So to multiply to be -3, it's either 3 and -1 or -3 and +1. So not really a whole lot to think about there. That's going to work out for us. All right, feel okay about that? In the bottom, you go, the bottom, actually, they both have x's, so we factor out a 3x. Sorry, I didn't say that correct or thoroughly. They both have an x, and they both have a 3. Right, the 6 has a 3. That's a factor. So we have x plus 2 left over. This one's pretty involved because, how many vertical asymptotes is he going to have? 2. How many x-intercepts will he have?
2.
How many y-intercepts will he have? None. 0. That was a trick. That was just a trick. Trick. Not a trick, really, but that term there tells you that there's not going to be a y-intercept. So, does that make sense to everyone? I'll elaborate further when we get to that step, but think about that. That means there's no y-intercept. So let's get into it here. We have the domain. Sorry, this marker's terrible. It's distracting me. But you still, I don't know, maybe has some purpose later on. Oh, that's a better marker. Okay, the domain. X can't be -2, and x can't be 0. All right. Are we all okay with that? Are there any questions on that? All right, good. That leads us to the vertical asymptotes. So there's going to be an x equals -2 vertical asymptote and an x equals 0 vertical asymptote. No one's got any questions on how we're going from here to here, right? Hopefully not. Pretty direct road there. Let's get the x-intercepts. Keep in mind, guys, x-intercepts are points. So every x-intercept is a pair of numbers, parentheses around them. I was noticing in the other class, I was seeing sort of frequently like that. The x-intercept is not a number. It is a pair of numbers. It's a point. Okay, so first one is going to be at 3, 0. So if you plug in 3 for your x's, 0 is your y. Everyone cool with that? And then we also have -1 would also get us a y value of 0. Let's get the y-intercepts. How do I find the y-intercept? Just plug in 0 for x. That's all you got to do. Easy peasy. Now this one is a little difficult to look at. Oh wait a second. You can't plug in 0. Wait a second. You're not allowed. Not in the domain. I need to erase that and say, now that's normally how you do it, right? Normally you plug in 0 to see what comes out. And most of the time you want to plug that into your non-factored version, just makes it easier. But in this particular case, there are none. It gets into one of the most common misconceptions of like horizontal asymptotes. Like, can you vertical asymptote if you're a function behavior? Okay, so let's go over this method here where you say, who's the x squared? Okay, so that means n behavior for large x values, my y value will be approximately equal to what? 1/3. Suppose x was 1,000,000. You'd have 1,000,000 squared over 3 square millions. So, or if x was 1,000, you'd have 1,000,000 over 3,000,000. You get the idea, hopefully. So the ratio here is the bottom will be roughly 3 times larger than the top for large enough x values. So let's summarize that. As x approaches infinity, y approaches 1/3. As x approaches negative infinity, y approaches also 1/3. Doesn't matter if x is negative or if it's positive. Farewell, Miss Caps. Miss you. She really snuck in there. Man, I almost could have been undetected. I know. Stealth. Splinter Cell. Tom Clancy's Splinter Cell.
I gotta wear clothes on.
Stealthy. There are stuff you want to be stealthy.
Okay.
Space is not stealthy.
Space is not stealthy.
Nah. It's colorful.
Outer space?
I mean,
Outer space itself is everywhere, so I don't think it's that stealthy.
Okay, so now we're just going to carefully put everything on the graph. So vertical asymptote at -2. Vertical asymptote at 0. There we go. X-intercepts, we got 3, 0. We got -1, 0. We got a horizontal asymptote. Remember this, you can summarize that very saying that there's a horizontal asymptote of y equals 1/3. So 1/3 means that our graph is going to, on the far right and the far left, it's going to be very flat, and the y values will be approximately 1/3. And what else? Like these intercepts, for example, are any of these ones bouncy? No. The term that produced this intercept does not have it's not squared or 4th powered or 6th powered or something. It's a 1 power, so it's going to pass through at 3. It's going to pass through at -1. Same with the asymptotes. The terms that generated the asymptotes are not squared, so they're not going to do this. They're going to do this. They're going to go the opposite direction. So, okay, let's see. What do you want to do first? Left, middle, or right? Middle, sure, middle. I picked the hardest one, geez. I would not recommend that, because I recommend starting with the easier one, but if you really want to start with the middle, you'd have to maybe make some. Do you see how there's only 2 options? It's either going to be this, or it's going to be this way. Okay, I can't do the bounce, for example, for the reason we just talked about. For this one, it's going to turn out, I believe, like this. Which is, a little tricky, but if I plug in, what kind of number could I plug in if I want to confirm that it's positive right here? -1/2. So if I plug a negative 1/2 into this, I'd have a negative number, a positive number, a negative number, and a positive number. Does that make sense? Which of course is a positive number. If I go negative times positive over negative times positive, that would be negative. Or I'm sorry, it would be positive. So anyway, on the right-hand side, I know that I have to pass through this point and I have to approach 1/3. So I put my end behavior in. I don't really have any other option except to pass through this point and then approach the vertical asymptote. Do you guys see that behavior at the asymptote that I was talking about?
No.
No, you don't see it? So, okay, so there's two kinds of asymptotes, vertical asymptotes. This type of asymptote, actually, let's do it with a different number. So we'll look at the difference between 1 over x minus 4. There's an asymptote, of course, at 4. This one's kind of an easy peasy because he's the 1 over x function shifted right 4. Right?
Yep.
Look at that. Look at the asymptote. They go in opposite directions, right? They positive infinity and then negative infinity. So they're going in opposite directions. But if you looked at 1 over, say, x minus 4 squared, that's different. That looks like this. See how the asymptote, they go in the same direction. So when you're looking at one of these functions, you can see the term that generates the asymptote determines the type of asymptote it is. So like if this had been x squared right here, there'd be a little 2 there, then they would be going in the same direction at 0. Oh, listen, yeah, just. Yeah.
I get it. I have a question.
Yeah.
On the first little line that you did, you're allowed to pass the horizontal.
Correct. Yep.
Is it like that on like every single one of them?
Yeah, so a horizontal asymptote, think about where this comes from. The horizontal asymptote really is just a statement about the end behavior. And the end behavior is just a statement about what happens when x is extremely large. So then logically, does the horizontal asymptote tell us anything at all about what's happening when x is like small?
Mhm.
No. The horizontal asymptote is only a piece of information about large x values. It's long-term behavior, okay? So, like, here's another quick example. So you could have something, you have some system where for whatever reason, long term, that in the long run, here's a good example. It could be temperature. This could be temperature of some object. Hey, here's a block, whatever. And a bunch of stuff's happening to it. And then here's the room temperature. Let's say this room is 70 degrees. And you set the block in the room and maybe stuff's happening to it, maybe some weird stuff. But long term, it's going to approach the room temperature. So that's some asymptotic behavior. Like, yeah, I can cross. You can go up and down. I can cross it. Doesn't matter. But long term, if I know that the temperature is approaching 70, then that's what I mean that's what we mean when we say horizontal asymptote. It's the end behavior. So, and then I guess while I was talking there, I put in the leftmost part of the graph. Again, I just based that off the end behavior. I said, well, I know that it has to approach 1/3, and it can't cross the x-axis because there's no x-intercepts over there. You have a question?
Yeah. So you know how the left side is above 1/3 and the right side is below? That's when you just like plug in numbers, right? You see this below or above 1/3.
I wouldn't get too concerned about that. That's a great question, though. Yeah, like, could this graph have gone below 1/3 and then come back up and approached?
No,
Yeah.
Not like that, but like, you know how it's like this and instead of that?
Oh, instead of being like this?
Yeah.
Oh, well, we could rule that one out. Like, how do I know it's not this?
It doesn't cross the x-axis.
Yeah, we've already listed out all the x-intercepts So then we know there's no way we can cross this axis to do that. Does that make sense? Now, what I think you're talking about is sometimes you've got, like, say the asymptote was 0. So say you knew in advance that, like, y equals 0 is the asymptote, and you were doing some graph, you're like, oh, am I above or below? Then, yeah, I'd probably just plug in a number and see if it's positive or negative. That's if you're like, what's talking? He's talking about, say you're graphing something, you're like, do I have a curve like this or do I have a curve like this? Which one is it? You a lot of times you just plug in a value and see, is my y value positive or is it negative? Okay, let's go over 33. All right, now while I'm erasing here, look at that question. Don't shout it out if you know it. I want everyone to think about this one. This one is a little different than everything else we've done so far. Ask yourself, what makes this one so different? Sarita, also I said, Sarita, don't shout out the answer. Keep it to yourself. It's not obvious. It's not the fact there's an H there. There's been other ones with an H. Okay, so are you saying you know the answer? Okay. Keep thinking about it. It's a subtle difference, but it's going to have a huge effect on the behavior of the graph. All right, Seth, what's the answer? Very good. That's a great answer. Could someone phrase that a different way? Yes, the domain's all reals. What did you say? Sorry, I didn't catch that.
I said the vertical asymptote there not is.
You're right, I shouldn't have asked. Okay, no, Eddie, that's very good. The domain is all reals. Okay, so we look at this. Now let's say I'm like, what are you talking about? Well, usually we ask a question: what x value would make the bottom of my fraction equal to 0? So let's ask that question. Is it possible for x squared plus 1 to equal 0? No, because x squared would have to equal -1 unless you want to start introducing imaginary numbers, which we're not going to do that. No solution here. So this can't be done. So therefore, the domain is all reals, which then, what Seth said, that means there are no vertical asymptotes. So this is the first question we've done as far as rational. It's the first rational function we've looked at that doesn't have vertical asymptotes. So we can still get all the other stuff. Let's get the x-intercepts. So again, now don't let that scare you, right? Everything else is the same. It's the exact same logic. What would make the top of my fraction 0 to make the whole thing 0? -2. To get my y-intercept, it's the same thing. I just have to plug in 0. What do I get when I plug in 0 here? 2. Let's get the end behavior. So I'm going to do my same technique where I go dominant term on top is x, dominant term on bottom. I can simplify that to make this statement that my y values will be, my function is roughly equal to 1 over x. Again, that's only true for large x values. Okay, so again, way off to the right side of the graph and way off to the left side of the graph looks a lot like that. Okay. So what that means, again, is if I graph that graph, then I'm very careful to realize that I'm just talking about these ends. I know that on the far ends, it looks like that and it looks like that. Again, this doesn't tell me anything about the small x values. Okay. Oh, by the way, so what kind of horizontal asymptote is that?
0.
Y equals 0. Very good. All right, so then I go like this, graph. I draw in my horizontal asymptote. I draw in my my x-intercept is -2, 0. My y-intercept is 0, 2. Is it helpful for me to do this, or is this wasting my precious energy? I mean, just to help keep that in mind. X value goes first. Y value goes second. Okay, so how's this going to fit together then? Can anyone see it? Can you see it?
No.
Yes, you can. No vertical asymptotes, so it's continuous the whole way.
Yeah.
It's going to approach 0 from the bottom over here, and it's going to approach 0 from the top on the right side. So try to put that all together in your head. How's it going to continuously approach 0 from the bottom over here? Okay, and then approach 0 from the top over here. How's that going to work? Well, it has to go up and then come down. Okay? This function was very interesting for the study of calculus because once you start getting into calculus stuff, you can answer questions like, say, what's the range of the function? So this is kind of an interesting function because the domain's all real numbers. It's an infinitely large span of numbers, but the range is just this narrow band of values. And then, which is something you learn in the calculus course is how do you actually figure out these humps? How high and how low are the humps? And where do they occur and stuff? Anyway, any questions on that? What?
Why is it so curvy? Why
Curvy?
Why curvy?
Actually, that's a really interesting question. I would say it's very uncurvy because, well, have you noticed that, like, a lot of times we'll graph something, like say this one. Is there anything that we have studied that would rule out the possibility of it looking like this? Like, I don't know if you thought about this, but there's nothing really stopping it from looking like that.
That's even.
But it's kind of interesting how they always end up looking so elegant and smooth.
Except for I don't have smooth hands, so they look like that anyway.
Yes.
Okay.
Yours is smoother than mine.
Here, let me
This
see.
one wasn't bad. This one wasn't bad. They gave
Some people though, they're drawing their graphs and it looks like they're like operating a jackhammer while doing their math. And I'm just like, I don't know. I guess your hand's that shaky.
That's how these problems were found. Someone was trying to draw a regular graph and then just started doing this and then made a problem.
Like, wait, what would this be? Let's figure it out.
Well, I don't know. It's interesting stuff, but okay. I hope that all makes sense. So again, this is not the case. Interesting how they almost always end up being the simplest possible graph that fits the description. Usually is the result. Some exceptions out there, I'm sure.
You should